if you have a pendulum, this is a pendulum, mass m, length L, then you can derive, which I do in class, but I won't bore you with that, you can derive how long it takes for the pendulum to make one complete oscillation. And we call that the period of the pendulum. And I derive in class that that period equals 2 pi times the square root of L over G. You already know what L is. If you don't know what pi is, you might as well leave right now. And G is what we call the gravitational acceleration, which is approximately the same everywhere on Earth, but it is very close in Boston to 9.80 meters per second per second. And you will say, well, that's weird, meters per second per second. What that means is that if you have an object and you drop it from a very large altitude, very high, a few hundred meters high, and I dropped it with 0 speed, after 1 second, it will have a speed of 9.8 meters per second. But after another second, it will add to that 9.8 meters per second, so it's twice that. And after 3 seconds, it's 3 seconds. So now you understand why it is meters per second per second. And so that's the meaning of G. There's something weird about this equation. Something that must go against your intuition. And you shouldn't feel bad because it also goes against my intuition. So we have the pendulum. And suppose I bring the pendulum all the way out here. We call that the amplitude of the pendulum. And we let it swing back and forth. There's a certain period. But now we bring it out only this far. It doesn't have to travel very much at all. Doesn't that make a difference in the period? The equation says no, it doesn't. Because if it did make a difference, there would be in that equation the amplitude, which is not. And I'm going to demonstrate that to you, that it is quite remarkable that indeed that period is independent of amplitude if you don't go to extreme values of the amplitude. There's something else in here which is even more non-intuitive. And that is, doesn't it matter whether the bob, we call this the bob, whether it is 1 kilogram or 500 kilograms? You would think, wow, that must make a difference in the period. But the equation says, sorry, it doesn't. And I'm going to demonstrate that to you too. We have here, by the way, if you ever want to test this pendulum, this equation for yourself, put in L equals 1 meter. And use this number, you will get a period of 2.0 seconds. It's very easy to do at home. You make one meter, you put an apple at the bottom, and you swing it. No, the 1 meter has to be accurate. You see that it's going to be 2.0 seconds. Our pendulum that we have here is really the mother of all pendulums. Look at it. 15.5 kilograms, and the length of this pendulum is 5.21 meters. However, you must understand that it is very difficult to measure that to very high accuracy. And so there is an uncertainty in the measurement of the length that we have to be honest about, because we are physicists after all. And the uncertainty we estimate is about 5 centimeters. So we could be off by 5 centimeters. That means that is 1%, 5 centimeters is 1% out of 521. But since L only shows up as the square root, it means the uncertainty in the time that we predict is only 0.5%. And if you don't see the reason why the 1% becomes 0.5%, that's okay, then just forget about it. You take my word for it. So now I can make a prediction. So I predict using this equation. That's all I do. I put in 5.21. I put in 9.80, I multiply by 2 pi, and I make the prediction that the period of that pendulum is 4.58 plus or minus 0.02 seconds. Why the plus or minus 0.02? Well, that is the 0.5% uncertainty due to the square root of L. And you can immediately see that 2 is about 0.5% of 458. So my prediction can be no better than that. Now comes the problem. I have to measure the period to convince you that it is independent of amplitude and to convince you that it is independent of mass. So the biggest problem now is Walter Lewin himself, which is my reaction time. How accurately am I able to make that measurement? That has nothing to do with our lack of knowledge of the exact length. Now, the last time that I gave this lecture with the pendulum is 12 years ago. I was 63. And at that time, I told the class, my reaction time is 1/10 of a second. And it was. But now I'm 75. And so my reaction time is no longer 0.1 seconds. What is it? Well, I do not know, but I have a feeling that if you want to be kind to me for a change, let us assume that my reaction time at age 75 is now 0.2 of a second. So if you can live with that, then every measurement that I make, no matter how long it is uncertain to 0.2 of a second. Do not confuse that with that 0.02. That has to do with the length. All right. So, I'm going to first make a period measurement at 5 degrees and then at 10 degrees amplitude. And I'm going to measure 10 periods, not 1. Some of you may think, well, isn't that a waste of time to do 10 periods if you can get away with 1? You will very quickly see why it is 10. You will see that. So the 10t is then going to be some number plus or minus my own inability, which is my 0.2 seconds reaction time. I can't change that. And so then I do it at 10 degrees, and then we get again 10t. We get a number, and then we get again plus or minus 0.2 seconds. And I'm going to demonstrate to you that within the uncertainty of the measurements, that I get the same numbers in all 3 cases, within the uncertainty. So, if you're ready for that, you see here the timer, that all of you can see. And here you see the pendulum. And I have 2 marks on the floor here. If I hold the bob here, then it is 5 degrees. This is 5 degrees. And when I hold the bob here, it is 10 degrees. Timing is not easy. The best way to do it is to start the timing when the pendulum comes to a stop. That is rather well defined. And then you let it swing 10 times, and then when it comes to a stop, you stop it. And it would help me if you would count how many oscillations we have made. Because then I don't have to look at it. All I have to do is when I come close to 10, I have to watch for the moment of stopping, and then I will end it. So, we'll do this first at 5 degrees. I'm going to start it when it comes here. Yeah! Okay, now you count.
1, 2, 3, 4.
You're doing very well. You're going to pass this course.
6, 7,
45.7. So that becomes that t. That means this whole equation now has to be divided by 10. And now you will see why I measure 10 oscillations. So t is going to be 4.57 plus or minus 0.2 divided by 10. That is plus or minus 0.02 seconds. And you see, comfortably within the prediction. So maybe my reaction time is a little better than 0.2 of a second. Don't count on it because you haven't seen the rest yet. So, now 10 degrees. Yeah. That moment is crucial. That moment is crucial. That's where you can lose 0.4 of a second, and then you look like an idiot in front of your students. Yeah. Now comes the hardest part. The hardest part is that we have to change the mass of this object. And the way that I'm going to do that is prominently demonstrated on the cover of my book. Yes, I'm going to hang on that pendulum. It is a difficult demonstration. First of all, it is painful. It really is. Second, the timing is tricky. Because when you look at a pendulum and when you see it stand still, you know, that is really well defined, plus or minus 0.1 seconds. When you are swinging yourself, however, then you can only do it by sensing the moment that you think you stand still. And that's what I will do. And then you will do the counting. And this is very unpleasant. It is. Oh, there's something else I haven't told you. If you're a good physicist, you will say, if you're going to sit on that bulb, then effectively you bring the mass of the bulb up, and so the length of the pendulum will shorten, and so you get a shorter period. And I know that too. Therefore, I will have to stretch my body so that when it is here, that it is almost completely parallel to the floor. If I don't do that, I will not be able to convince you that the period is independent of the mass. And that makes it very difficult for me. So I will start it at some moment, you will see when, and then you do the counting. Are you ready? Okay. Yeah! You count. This happens sometimes. And in fact, nobody knows why. Have to start all over. I did not stop it, I really didn't. Oh, it's still counting? Okay, I have enough energy to give it one more attempt, but not to give it two more attempts. Okay. You ready? Okay. Oh, this really hurts. Can't you count a little faster? T with Walter Lewin. What is it? 45.9 plus or minus 0.2 period is 4.59 plus or minus 0.02. I told you, physics works. If I have a tennis ball in my hand, and I drop the tennis ball from a certain height, give it no speed, and it will bounce back, then it can never bounce higher than where it started from. If it did, then we physicists would say that is a gross violation of the conservation of energy, and that is the holiest of all laws in physics. It cannot go higher. Suppose the object has a mass m and is a distance h from the floor. Here's the floor, here's the object, h. We associate with the position of that object an energy that has a name. We call that potential energy. And that potential energy is mgh. You already know what g is. Well, h is this distance in meters. So when the object is here on the floor, h is 0. So there is no potential energy. As the object goes down, it picks up speed. And we associate with speed energy, which we call kinetic energy. And the kinetic energy of an object with mass m is 1/2 mv squared. M is the mass, and v is the speed of that object. If the object goes down and it hits the floor, then the potential energy is 0, and all that energy is now converted to kinetic energy. Because energy, we believe, is conserved. Now, when it hits the floor, some of that kinetic energy may be converted into heat because of the compression. If it were a tennis ball, that would certainly happen. So in other words, when it bounces back, the total energy is no longer the full mgh, but is a little less, and so it won't bound as high. But there is no way that it could come up higher than h. Suppose it could come after one bounce up here. Well, that would solve the world energy problem. Because you simply sit down and you watch the ball game, and there goes the ball higher, and the second one, it goes again higher. But why? If it goes the first time higher, it will do that the second time. And so after an hour, that thing is about a few thousand meters in the sky, and when it comes down on the floor, it has an enormous speed, great amount of kinetic energy, and so you got energy out of nothing. But there is no such thing in physics as a free lunch, so that's not going to happen. So the object can never go any higher than h. And with a tennis ball, there is also what we call the dissipation of heat when it hits the floor. Now, the situation is difficult with a pendulum, because a pendulum doesn't hit the floor, and so there is no heat loss because it doesn't hit the floor. So if you bring a pendulum at a certain distance above the ground, like this, and you let it swing, when it comes back here, it is almost exactly at that same height. Cannot be higher. That would be a violation of the conservation of energy. But since the air drag is so small, there is almost no damping. And in fact, when you saw the demonstration I just did, you may have noticed that you really didn't see this. It really kept going and it kept going. As long as you realize that if I release it from a certain location with zero speed, it can never, when it comes back, be higher than that location. This whole idea is behind demolishing buildings. With a building demolishing, you take a huge mass, you lift it up over a distance h, and then you put your target, which is your house or whatever it is, right at the bottom, when all this potential energy is being converted to kinetic energy, and so this object is hit with an enormous amount of energy, at high speed, and you demolish thereby the wall. Here we have a glass plate. You better go out of the way because this is a dangerous experiment. This is a glass wall. So if I bring this object exactly at that glass wall, and if I'm clever enough to let it go with zero speed, it could not break that glass. But if my hands shake a little, and if I give it a little push, then of course it can come back, and it may want to go higher than this, and that would mean I know you guys. Students love it when the glass breaks. That's why they pay such a high tuition at MIT. That's okay, just take that off. Now comes an experiment which is emotionally the most difficult for me of this whole evening. I'm going to put my life on the line to show you that I'm really a believer of the conservation of energy. And you will see how I'm going to do that. I'm going to take the place of the glass. And I'm going to hold this object at my chin. And I cannot move any further back, so there's no cheat here. I'm going to release it right from my chin here. You realize, as you have just seen, that the slightest push, and this will be my last lecture, and no book signing afterwards. So I need your collaboration. When I count down from 3 to 0, no noise, no coughing, and I would even appreciate it if for those 3 seconds you would not even breathe. And I have to tell you something. I couldn't sleep all night. I'm going to close my eyes. I don't want to see it. And I'm going to count down from 3 to 0. 3, 2, 1, 0. I normally, after this demonstration, tell the class, physics works and I'm still alive. And when an article was written about me in the New York Times a few years ago, on the second page of the New York Times is the wisdom of the day. And the wisdom of the day was, physics works and I'm still alive.